So tomorrow we'll start with the quiz. I think it's 10 question limiting reactants, and it is on your Chromebook on quizzes. On Friday, I will not be here, and Miss Coker will be here, and y'all will have a writing assignment that needs to be done. I know y'all may be getting tired of writing over the next couple of weeks, but it is a really easy way to get 100 on that grade. So that's a good thing, if you can think of it that way. Because y'all will just be in here for a short period of time. Thursday, we'll do our lab, and there's not really a bunch of lab right up with it, so hopefully you'll have a chance to get through with all that. I won't see y'all Monday, so Tuesday when y'all come in, we will do our test. It is on paper. It is over the stoichiometry unit. It's all problems. You have to show your work on the problems to get any kind of credit. And Ben and Jaheen, I sent an email to all my virtual students this morning talking about that as far as showing work. So please make sure y'all read that. And Wednesday will be our journal test. And then that should round up the 6 weeks. And then we'll be down to 2 6 weeks. All right. So on my journal today, I said that when we do, or when a chemical reaction, because we study them because we're studying chemistry, but in real life, chemical reactions are done all the time for various reasons. The very probably most easiest way to think about it is that chemical plants to produce a product that they're going to sell. And you can figure out by stoichiometry how much of a product should be made if I start off with a given amount of reactants. But usually, in real life, less product is made than what we calculated it to be. And my question to you is, what could a possible reason be? And you get less product than what you think you're going to actually get. All right, well, then I'll just let y'all think about that and y'all can finish that out.
Want us to answer?
I would like for somebody to try.
I said because if there's less of a product and it's like in high demand, there's like more, they want more of it, and if they have less, they don't have to worry about like the waste.
Okay, that's one economical way to think about it. But I guess my question is, Francisco? Let's say I did this reaction, it's been a while ago, I haven't cleaned up yet, I guess I'll be doing that tonight. And that was magnesium hydroxide down there. So let's say that I wanted to capture that magnesium hydroxide, that I wanted to keep it, that was some product I'm trying to sell. And I know how much magnesium hydroxide should be in there because I could have calculated that. What would be one reason, and there could be more than one, what would be one reason that I might not capture that whole amount of magnesium hydroxide that I might want? That's what I'm trying to get at. Yes, sir.
Is it kind of like energy? Like if you put energy into something, you're not going to get the full.
No, it's actually, you're thinking like a lot harder than you have to. It's really, so let me ask you this. If you make cookies and your recipe says you're supposed to make 3 dozen cookies, and you make your cookies and you make them the right size, but you only make 2 dozen cookies, why do you think that happened? You made a mistake, right? Human error. And don't you think that human error happens in real life? So that could be probably a really obvious one. Human error would be one. Yes, sir.
There could be impurities that affect the reaction.
There could definitely be impurities that can affect the reaction. Slow it down maybe, or maybe take away some of the reactant. What about if you're making cookies and somebody scrapes a bowl with a spoon as compare scraping the bowl with a spatula. Stuff is left behind, right? Same thing could happen there. You could have your product left behind. We're going to talk about some other reasons that are kind of a little bit more complex in an AP chemistry than we really talk about it. But kind of just some basic things would be like human error, or as easy as some of the product being left behind. Obviously, if you work in a chemical plant and you're producing some expensive product, probably aren't allowed to make too many human errors too often if you want to keep your job. And I'm assuming they have some way to try to get all the product out. But those would be kind of just a couple of basic ways. All right, let us finish these stoichiometry notes. And I promise you, nothing today is 3 steps where you have to do 3 stoichiometry problems. So we've done the longest. There will not be an excess problem tomorrow. It was just put in on quiz. There's no way really to do that, but there will be an excess problem on the next Tuesday. All righty. Limiting reactant, we got rid of that. All right, so we're doing percent yield. All right, so we talked a little bit about the fact that we could set up equations and we can look at our stoichiometry and we could say what should happen in a reaction. But in reality, that's not actually what will happen. Sometimes, and it's really most of the time, reactions do not make all of the product predicted by our stoichiometry calculation. Some of the reasons why, besides what we talked about, many reactions do not completely use up the limiting reactant. It's just the fact that for reactions to actually occur, the molecules have to line up in certain position, or the atoms have to line up in certain position with certain energy. And when we write it out on paper, that looks real easy, but in real life, it isn't as easy. Some reactions are reversible. So once you start building up a lot of product, it'll reverse back and start going back toward the reactants. Most reactions, kind of like what Aaron said, will have to be purified to collect them. And this could be difficult. You could have some impurities that may cause some side reactions and use up some of the reactants. If I was really trying to get that magnesium hydroxide, my problem in doing that would be trying to drive off all the water. So I may even actually get more magnesium hydroxide than what I calculated, but it wouldn't be pure magnesium hydroxide. It would have water in it. Reactants or products can be leaked or spilled. That would be kind of a human error. They're not always 100% pure. And some reactions occur very, very slowly. And so they stop. So a little bit like what Francisco was talking about with the energy. So they stop before all the products are actually formed. So we're going to be looking at today what's called percent yield, the percentage of the theoretical or calculated amount that is actually made. So the theoretical yield is the expected amount of product from a reaction. It's the answer to your stoichiometry problem. It's your calculated amount. I don't know why this thing is so thick all of a sudden. So it's the best case scenario, assuming everything goes perfectly right and nothing goes wrong. That's how much you should make. But in real life, we get what's called the actual amount of product from a reaction. This can only be determined in the lab. It's what is actually made when the reaction occurs. So you're looking for words like produced, formed, isolated, and obtained. Those would be words you'd be looking for to know that number is talking about the actual amount. The actual has to always be given in the problem. The theoretical doesn't have to be given in the problem. If it is, then the problem is really easy, but you could also calculate the theoretical if you have enough information. The higher the yield, the better the results, and you can see companies would make more money because they're getting the more of their product that they want. So and when you're looking at percent yield, you're always looking at a product. In other words, I would not be interested in the percent yield of a reactant. That doesn't really make sense. So the formula, which is right there below, you can see it's really easy. It's just my percent yield is my actual yield divided by my theoretical yield. And because we want it in percent, we're multiplying by 100. So my units are going to be percent. And you still have to worry about sig figs. So when you start getting your start working on your calculations, your actual yield should be less than or equal to your theoretical yield. And it's usually less than. So what that means is if you do this calculation for percent yield and you get over 100, then you have probably flipped your actual and theoretical, and you need to flip them back. Now, I will say if we did some lab in our little lab setting, we may get a percent yield greater than 100. And once again, it would be because of trying to drive off water would be a big problem in our lab, or because of human error. But when you're working through your problems, they're supposed to be real life perfect settings. So you should not be getting a percent yield that is greater than 100. All right, so let's look at some problems. The first one's a little bit longer. All right, so this says zinc citrate is an ingredient in toothpaste that stops the growth of dental plaque bacteria by inhibiting their metabolism, in case you were interested. If 6 moles of zinc oxide react with 10 moles of whatever that hydrocarbon is, then calculate the percent yield if 990 grams of zinc hydrocarbon is actually collected. So the only thing I am not worried about in all of that is water. So this 90 grams of zinc citrate, 990 grams of zinc citrate, is that a theoretical or is that a actual? That is an actual. Because it says it's actually collected, and because the actual has to be given to you. So we don't have a theoretical, so we're going to have to calculate the theoretical. But besides having to calculate the theoretical, what other kind of problem is this? When I have two givens. The ones we just did, right? Limiting reactant. So since it's a limiting reactant, I have to do two stoichiometry problems. Find my smallest amount of product, and that's going to be my theoretical. At least this will be a little bit shorter because my given is in moles, so it's 3 steps instead of 4 steps. So one of my givens is 6 moles of zinc oxide, and the other one is 10 moles of, I'm thinking that may be citrate. I'm just going to put CHO to help be my placekeeper. My actual, what they reported to me was my grams of zinc citrate. So that means that has to be my unknown over here. Zinc cit. All right, so then we just start following our units. If I'm moles of zinc oxide, I have to be moles of zinc oxide down here. So this doesn't say anything about grams. So this is my mole to mole ratio. So how many moles of zinc oxide do I have? 3. And how many moles of my unknown, this product? 1. And then we would have moles of zinc citrate down here, and then you would have to figure the molar mass of that. I would definitely give you that molar mass if this was on the test. 574.39 per 1 mole. I got 1,150 because of sig figs, 3 sig figs. Y'all are my first class that checks my work. All right, and then I'm gonna do with my other reactant. Did y'all get, is that what y'all got? 1,150? Okay, so moles of CHO. So that would be 2. And then all of this, because all of this is from my unknown, that just repeats. So at least I would not have to figure out that big old molar mass again. 1 mole. And this was 574.39. And once again, 3 sig figs. And you have to be careful when you're doing a limiting reactant. Sometimes your 2 answer may have different amount of sig fig because one of your givens may be 3 sig figs, the other one may just be 2. I got 2,870 grams. So once I've done that, remember you're always interested in the smallest amount. So this is my theoretical yield. It doesn't ask, but if I came back and looked, my limiting reactant would be zinc oxide. So now I get to do the easy part of the problem. So my percent yield is going to be my actual, which was given to me in the problem, divided by my theoretical, which I had to work for, and multiply by 100. That actual only had 2 sig figs, so the 990, so my answer could have only 2 sig figs. So I got 86%. So what we're learning today, which is really this, is not that hard. It's sometimes the work you got to do to get there. Notice that when you're doing any kind of percent, they have to be in the same units. So if one of these happen to be in grams and the other one's in moles, I would have to convert them to get to the same units. Another thing, if I give you a molar mass on the test, because I'm giving y'all several throughout the test on really long, anything that's really long, I'm not trying to trick you. You don't have to go back and double check that molar mass, okay? So I'm just giving that to you to get to save you a little bit of time. All right, does anybody have any questions on that particular one? Where any of the numbers came back from? All right, let's look at the next one. This one says, if 12 grams of copper 2 chloride was actually produced, but 25 grams of copper 2 chloride was calculated as the theoretical, what is the percent yield? Do I have to even do any stoichiometry on that one? I'm given my actual, and I'm also given my theoretical. So this one, all I have to do is plug it into the formula. So I'm assuming this is probably how y'all would like all of them to be. My actual, which should be my smaller number, divided by my theoretical, already calculated for me. I didn't have to do stoichiometry. And simply multiply by 100. And we had 3 sig figs, so my answer should have 3 sig figs, so I got 49.2%. All right. Number 3, a chemistry student uses 25 grams of lithium sulfate to react with excess barium nitrate. If something's in excess, then that means it's not part of this problem. It means it's not a limiting reactant. The student isolates 43.5 grams of barium sulfate. What is that 43.5? Actual, perfect. So we are going to have to calculate the theoretical, but it's not a limiting reactant, so you don't have to do 2 problems. So I want y'all to give this one a try, going all the way to percent yield, and I'm going to give you a couple of molar masses to help you out. I'm going to write them up here. So, because that's kind of what takes a while. 109.95 grams per mole and barium sulfate. Hello. 233.40 grams per mole. All right, so I'm going to erase this. All right, so there's a couple of molar masses you're going to need because you're going to have to do one stoichiometry, gram to gram. Remember, our product that we're interested in is barium sulfate, so we're not interested in lithium nitrate. So when you do that, that'll give you your theoretical. And then you can do that last calculation, and those 2 molar masses should kind of shorten it for you a little bit.
So gram to gram is
4. It's going to be 4. All right, who got me in percent?
I got 53.07.
53.07. Anybody else? 81.9. You know what? I think you did, Carmen. I think you just stopped too soon because this or 53.1 was the answer to your stoichiometry problem. But then you needed to take that. See, because remember, we were actually trying to figure out the
I thought
percent
you meant for this
for the other.
one.
Okay,
I
so
got
what you get for
80
the other?
I
Okay,
got
perfect.
82.
Yeah, because then that's just a little sig fig issue. So, but we'll talk about that. Perfect. All righty. Okay, so we have 25 grams of lithium sulfate, and we need to get to grams of barium sulfate. And so needed a molar mass here, so I gave it to you, which definitely makes it a lot quicker. Grams per 1 mole of lithium sulfate. And then here we have moles of lithium sulfate. So this is where I'm doing my moles of my known, which is just 1, and my moles of my unknown, also 1, right? And then finish it out with moles of barium sulfate. And I gave you the molar mass, 233.40 grams per 1 mole. And then we just multiply across, and the only thing we have to divide by on the bottom. And this is 3 sig figs, so my answer would be 3 sig figs. So that's just where you got just a little bit off. And remember, that's my theoretical. So then simply to finish it, I would take my actual, which was given in the problem, divide by my theoretical, which I had to work for today, or that for that one, and multiply by 100. And my answer should have 3 sig figs, so we got the 81.9%. So hopefully that does not seem as bad as the limiting reactant problems. So y'all got about 10 minutes to work on some of them. You got some practice there in front of you, not too much. We will not have an individual quiz on this. So you will just see it on your test on Tuesday. I think there's a couple of problems from this. Limiting reactant, yes. Yes,
How do
ma'am.
you know which ones are actual?
Well, the actual always has to be given to you, and it should have some hint word like. Let me pull y'all's practice up. See, like on A, 15.5 gram of NH4CO react. So that means it's a reactant. So that can't be your actual. Remember, your actual theoretical always has to come from a product. So in the reaction, 35.5 grams of silver chloride is produced. So that's your actual. You're going to have to write the equation and then figure out your theoretical on that one. But double check, make sure it's a product. And then if it's only one, it's going to be your actual. If there's two, if they give you 2 amounts like that one that we did up here that was so short, then one of them is going to be actual and one's going to be theoretical. So then choose your smaller number for your actual.